Um, but anyway, so Daniel, of course, the famous one of the family, um, was credited with the idea of these two expressions. One along a streamline, which allows us to be able to write behavior at two individual points in terms of 6 variables: pressure head, elevation head, and velocity head, which in turn match with the F part of F equals ma, pressure head and elevation head. And the mass times acceleration is the velocity head, and that element, if you like, comes from destruction of velocity. Destruction of velocity with air on someone's chest makes a pressure. So you trade one for the other. And so we talked about how if we can define behaviors at 2 points, and if we only know one unknown out of those 6, we can solve for it. If we don't know 2 of the components, we can typically invoke something else, which is continuity, which is that volume in equals volume out, or really mass rate in equals mass rate out. And of course, if the mass doesn't change of the fluid that's flowing, that's the same as volume rate in equals volume rate out. And we can use that to be able to link the upstream and downstream velocities, and therefore substitute into Bernoulli's equation to be able to do that. And we also talked about going across streamlines to be able to determine how fluid pressures would be, with the kind of net effect that if you're going over a hump, then if you go down through the fluid profile, the change in pressure with depth will be less than it would be in static fluid. And if you go through a trough, like a ski jump, water being forced out at the bottom, let's say the tail race of a dam, then the pressure change with depth would be greater than the linear pressure profile as you go down in a static fluid. So we talked about applying that in a variety of different locations. So today we're going to talk about pressure measurement of flow rates.
Discovered the direct relationship between the pressure and speed years ago. Swiss mathematician and physicist Daniel Bernoulli discovered the direct relationship between the pressure and speed of a fluid flowing in a pipe. Italian physicist Giovanni Battista Venturi also performed experiments on flow. And in 1797, he built the first flow meter for closed pipes, known as the Venturi tube. Here is how this measurement method works. Differential pressure flow meters have an artificial restriction integrated into the measuring tube, illustrated here by the example of an orifice plate. 2 holes are located in the pipe wall, one before and one after the orifice plate. 2 separate tubes connect these holes to a differential pressure sensor with its 2 pressure chambers separated by a diaphragm. The tiniest pressure differences in the flowing fluid can be precisely measured. If the fluid is not flowing, the pressure before and after the orifice plate is essentially identical. As soon as the fluid starts to flow, its velocity around the orifice plate increases significantly because of the restriction in the cross-section. At the same time, due to the laws of fluid mechanics, the static pressure at this point decreases. Consequently, different values are detected in the pressure chambers of the sensor, a higher pressure before and a lower pressure after the orifice.
Becomes a bit elementary, I guess, after a while, but you think you get the idea. How's it go on? I didn't really look at it. Yeah, so some nice pictures of flow velocities as you go through here. So what we'll talk about today is how we can use Bernoulli to be able to measure flow rates in systems. And of course, you could think about measuring flow rates by taking water and putting it in a bucket, seeing how long it takes to fill a bucket. The bucket has a given volume, and you can use that then to be able to calculate what the discharge rate is. So you could do that, but it's typically not very easy to do that because you have to interrupt flow. There are some devices that measure that in that way, and the ones that I can think of would be things like a gas meter for gas coming into your house. These big gray boxes you see sometimes attached, you have 10 of them in these townhouses to be able to supply 10 different townhouses. You know, these gray metal boxes about yay big, which basically take gas comes in, it fills up a chamber, and then that chamber changes shape, and then opens a valve, and it meters out that volume that goes into the house. So it has some moving parts in it. It used to be also that when gas was pumped, I'm not sure how they do it now, but you'd see on the side of the gas pump a little hemispherical dome, which was plastic, polycarbonate, clear. It would have a little bladed rotor in it. So it would have maybe four compartments which would fit in it. It would have a vertical axis, and as gas came in one side, it would just move it around as a metering. So it would take this quadrant, full of gas, and it would move it around from the side that was coming in from the pump into the side that was going into the gas line and into the vehicle. And so those are methods which actually provide some kind of metering, but typically more commonly in use are methods that would use Bernoulli's equation in some way to measure flow rates, in other words, the V term in the Bernoulli equation, by one of two ways. The other two available terms are either fluid pressure or elevation. And so in different applications, you'd use either fluid pressure, as in the Venturi flume, in a pipe to measure flow rates, or you'd put a weir across a stream and measure the height of the stream above that weir and be able to use that as an indication, if you like, of the water flow in the system. So this is the idea. So, I mean, these vary from taking a low head dam that goes across the Ohio River, where you can measure the stage, the height of the water above that, to be able to say what the flow rate is down the river, to taking into the field a piece of plywood that has either a rectangular notch cut in it or a V notch, putting it across a stream, measuring the height of water in that notch above the bottom of the notch, and using that directly to be able to calibrate for the flow that's in that stream when it's unimpeded. And so those are the methods that we'll talk about today. Don't want that yet, so I want this. So that's kind of where we are. And so we've talked about these things in the past. We've talked about along streamlines and normals to streamline. Just kind of reasserted that in terms of the three components that we deal with. We've talked about free jets in terms of velocities in systems defined by the driving head, driving a velocity across the system. And we've also talked in the past about how we use continuity together with Bernoulli for the cases where we're missing a variable to be able to constrain the system, where we have two unknowns and only one equation. We need to have two equations and two unknowns. Okay. So our parting shot on this will be talking about flow measurements in terms of orifice meters, the most sophisticated ones of which are named after, apparently, the famous Italian physicist Venturi, and open channel flows in terms of weirs, both undershot and overshot weirs. And we'll also, maybe if we get to it, talk about the limitations of using Bernoulli's equation, which we said could only be used for incompressible flows. We've used it for air, seems to work okay. Talking about the spatial reference frame, which we've already actually assumed without really thinking about it, and also whether we can apply it to non-steady state flows, which we perhaps can. So let's see how we get through this. Basically, this is the idea. So when we talk about Venturi meters, this is just what we saw. The Venturi meter in the diagram was initially an orifice plate, and so I'll come back to that. But so long as you can obstruct flow in some way, either with an orifice plate that partially constricts flow from this width or to this width, then we know from what we understand about Bernoulli that things will speed up. And as it speeds up, there's always this trade-off between an increased velocity and a change in pressure, because it always has to be constant, those three terms. Typically, these orifice meters are made in such a way that the transition from the upstream to the constricted zone is desired to be as benign as possible. So a relatively slight gradient and also smooth. So these would give more eddies and more inaccuracy, if you like, in the system than something which is a relatively smooth transition between. So the desirable outcome probably is something like this, where you don't have these wayward and unpredictable eddies behind, which might make the calibration a bit more difficult. But the principle is relatively straightforward, and that is we'd like to know what the velocity in the pipe is here. We know that the velocity in the pipe will be different here. It'll be higher. And so what we can use is the idea of Bernoulli, which really takes, for instance, we could draw, what would it look like? If we drew along the length of this, these components, we have elevation, we have pressure head, and we have velocity head. So as we go along here, if we start off with elevation as 0, it's the same elevation all the way along here. What would the profile look like? We know that the sum of these, which we will call, which we have called, we'll call this H. So I guess that's already written there. So this magnitude here has to be H, and it has to be constant all the way through. And so we know that since this isn't changing, then any trade-off in terms of velocity has to be between these. So presumably this has a relative high pressure, which as you go along, I'm just mirroring this diagram underneath, where this would be, at any particular point, the pressure head, P over unit weight of the fluid. And this, as you could rationalize, would be the velocity head, V squared over 2G, and so on. And so clearly at this point here, velocity is increasing at the expense of pressure, and then it regrains this, where as velocity reduces, then pressure bounces back. And so I think the only inference of this diagram is that as you have small flow rates, then this dip in pressure, this reduction in pressure would be relatively small. In other words, this would be the zero velocity magnitude, I suppose, this horizontal line. As you increase the flow rate or the upstream velocity, and of course if this is V1, then the volumetric flow rate is just equal to the area at 1 times V1. Separate from this, right? And so you could imagine that if you increase the velocity high enough, you could get it high enough that it goes below the vapor pressure of water. And if it goes below the vapor pressure of water, then you'd get bubbles forming here. And then they would disappear downstream. But you probably wouldn't want that because it would add inaccuracies into your system. And so you want to avoid cavitation in these things. So you can design it, of course, to be able to avoid that, primarily by changing the taper so that you don't get the velocity to go so fast, or I guess by changing the cross-sectional area so that the velocity is sufficiently small that the pressure doesn't drop below whatever the vapor pressure is. So that's, I think, the only point that's being made in that figure. And so if you want to solve for the pressures or the velocities in the system, it's pretty straightforward. We can write our Bernoulli's equation between 2 points. If it's horizontal, it doesn't necessarily have to be horizontal, but we just make our life easier if it's horizontal. Then this is the appropriate Bernoulli equation. We don't know what this is. We don't know what this is. We'd like to know what either of those are. We only need to know one. But we do know what the pressures are because we want to measure them. We can either measure them with pressure transducers at the orifice and upstream or downstream of the orifice and subtract those pressures from each other, or we can measure it as the way they suggested in that little movie clip, is with a differential pressure transducer, which measures very accurately the differences in pressures but doesn't measure the absolute pressure, and it just measures it by having a pressure on either side with a membrane in the middle. Depending on which height is the higher pressure, the membrane will buckle in that direction, or the diaphragm will buckle in that direction. You measure the displacement of it with a strain gauge, and you feed it into a data acquisition system to be able to measure the pressure differential. And so we can get either the absolute pressure or more likely the differences in pressure. and we want to know what this velocity is. So we have one equation but two unknowns. We constrain those two unknowns by writing that in terms of continuity. And then I guess in this particular case, this must be flow rate as a function of this. So this must be, I won't do the manipulation, this must be V2, right? Area 2 times V2 is equal to flow rate, and which is also, by the way, of course, equal to V1A1. And so in this particular case, I presume that we've taken V1 as a function of just divide both sides by A1 and substitute this into this. If you do that, you now have this equation written only in terms of V2, because this term is coming here. And if you have it only written in terms of V2, you can rearrange it to be able to define the pressure drop across the system. And so you can then transform this to solve for V2 being equal to something, which is basically what this equation is here. Multiply V2 by A, and you have flow rate. And so it's just a matter of straightforward algebraic manipulation. And you'll note, of course, that you don't need to know absolute pressure. All you need to know is the differences in pressures between these two things. And so a high accuracy differential pressure transducer can be used. The great thing about, also I guess from a practical standpoint of a differential pressure transducer, is that it doesn't matter if the pressure is 1 kPa or 100 kPa or 10 million kPa. It's only measuring the difference in across the system. And so pressure transducers always have ranges, and once you get out of those ranges above them, you blow it. And so if you're only measuring the differential pressure, then you can be anywhere in a much bigger range. And so that's the advantage of having a differential pressure transducer. So that's how an orifice meter works, or a Venturi gauge. You could measure things with a pressure transducer. You can also measure them with manometry, with a gauge fluid in the system. This is basically the same application as before, trying to measure velocities directly. I suppose, obviously, you could, instead of having this arrangement here with a manometer tube which is looking upstream, you could also have a manometer tube that was just cut off horizontally, in which case it would measure the pressure between these 2 points. So in other words, you could cut off this manometer tube here and measure a pressure here, measure a pressure here. Actually, the height difference in this case would also be just registered by the differences in the gauge fluid height. And so this would give you a direct measurement of fluid pressure in that case. I guess what is called H would be equal to what? P1 minus P2 over the unit weight of the gauge fluid, which is mercury, I guess, in this particular case. Or you could do it differently, as in keeping this intact and having this pointed upstream. So, but the principle is the same in terms of being able to use it. If you had these tubes not pointing upstream so that you were destroying velocity, you could go ahead and just directly use this expression here, and you could put it into here, and you'd end up with the appropriate flow rate across the system, taking into account the ones and the twos, of course, the upstreams and the downstreams. And again, as we said last time, it doesn't matter to what we've done so far, but just out of protocol, we often use upstream as the left-hand side and downstream as the right-hand side of the equation. And we'll use that ultimately. If it is pointing upstream, you can also solve it, but you won't be able to use this particular form of the expression, because now you're not just measuring pressure at this point, but you're measuring a pressure that is due, not the real ambient pressure here, but the pressure that occurs due to the fact that you're stopping a velocity, and the fact that the velocity at this point, at this measurement point, has to be 0. And so it's a little more tricky than that. And so let's just go through it quickly and see what we understand about it. Let's take the middle point through here as we go through here. So the elevations are the same, so we don't have to worry about that, in which case we get rid of those two parts. We know that because it's saltating at this point here, the velocity at this point has to be 0, so we get rid of this. And so if that's the case, we're left with a differential between two pressures and one velocity in the system, which is this. So we have some system that defines this. However, we can't just substitute in this expression here for that. This would be the actual fluid in the flow field. So this would be, in this case, the flowing fluid, not the gauge fluid. And we can't use that in this particular case directly for this. So what else do we have to do? So we can use the manometer equations. So the manometer equations would be, take the pressure at point 3. We want to get the pressure at 1, so we go across to here, and then we increase the pressure by adding a height L times the fluid flowing in the system. So P3 plus unit weight L has to equal P1. This is also the same as the pressure at this point here, since we can go directly across here and make the same route to this point as well, just L1, is also the same as this. So that also follows, because P3 and P4 clearly are the same magnitude. We can also define the pressure here in terms of the system as well, and I guess in this particular case it would be what? It would be P4, which is this term here. We go up a height times, so subtract off H times unit weight of the gauge fluid. We know that we can go across to this point here. We go down a length which is going to be H plus L times the unit weight of whatever's flowing. So this clearly also is true. We end up at point 2, and we have this point. So we now have two pressures in the system. We have a velocity defined in terms of those pressures, and so all that remains is for us to substitute into here and to be cognizant of the fact that we have both a gauge fluid, which is mercury, and we also have a fluid in the pipes, which is not mercury. So we have gasoline flowing in the pipes. I guess it probably would be some oil, right, because it's lighter than water. And so if we substitute these pressures into here, we can solve for the rest of it and get something out of it. So I guess the trick is that the fact that this has a pressure which is no longer just a straight pressure that we're measuring, which is representative of the flow, but it's a pressure that's modified by the fact that we're killing the flow velocity and putting it equal to 0, and hence the reason we can't use this expression directly. We have to solve it slightly differently. Right? But the same principles. Trying to figure out exactly what things are just by figuring out what the individual components are. Okay? So, we have two free parameters out of our 3. We want to be able to measure velocity, v squared over 2g, to get velocity. We have a potential to measure pressure, which we can do with a pressure transducer, which is pretty easy if we have a confined flow. It's much easier if we have an unconfined flow to measure the z term. You could, of course, measure pressure. For instance, you could just put a pressure transducer on the base here, and that pressure transducer would, for instance, measure a pressure equal to unit weight times Z1, just a static pressure head. And so that would be one way would be to measure pressure very easily and use that to convert for a head magnitude. And sometimes that's used in wells and in oil wells and water wells. You measure pressure, and you can calculate the column height of fluid in a static well. And if it's flowing, you could also calculate that the change in the pressure that you have because of the driven flow in the system as well. But usually, rather than measure pressure and convert into an elevation, you'll just measure elevation directly. And so what you could do is you could put a weir across a stream. So this is the perspective of this, with this undershot flow, and then apply Bernoulli again to be able to figure out exactly what's going on. So you could take a streamline. Streamline is from one that goes underneath here, comes out and goes downstream. You measure this height downstream. You want to calculate either the velocity at this point or the velocity at this point. Probably easier to have this one because it's flowing faster. And you try and constrain it in terms of what we know. On the surface, by definition, the pressure has to be equal to 0, atmospheric. So the elevations we know because you can measure that relative, so we can get rid of this term and this term. So I guess it's the opposite of the other case. Before we had the elevations were constant along this center line of the Venturi flume, and the pressures were non-zero. And here we have the pressure 0 and the elevations are non-zero. So this is just Bernoulli's multiplied through by the unit weight of water on all sides, right? All terms. We would have knowledge of this, we'd have knowledge of this, but then we're left with two other variables for velocities. We don't know what those velocities are, but we can solve our problem of having two unknowns in one equation by just providing another equation, which is continuity. The area is going to be equal to Z1 times B, up here, right? So this is the area here. This would be the area here, area 2 and area 1, I guess. And so that's just given by these components here. And this, by definition, also has to be the same as flow rate, right? Just by definition. Flow rate is usually meters cubed per second. Cumex, I guess, is cubic meters per second. And so if you substitute for one of these for velocity 1 into this, I guess in this case, this also must be, just by looking at the form of this equation, this must be V2, because V2 times Z1 times B, this term here, has to be equal to flow rate. So this is area. And again, you can just straightforwardly get the magnitude of the flow rate from knowing what this downstream elevation is, height of the water, how wide the river is, and everything else you can measure. Upstream height of the system above here, and downstream height. Typically the assumption is that when this comes out, it's also roughly the same as this separation. Typically it's slightly less than it. It'll say at the bottom maybe 0.6 times this, just by so-called vena contracta effects, that this actually does taper down. But if you measure the height here, then you can figure out everything you need to know in this system. In the case that you make this height really quite small compared to the height of the water upstream in the impounded region, then in that case Z2 is much smaller than Z1, and if that's the case, then you'd lose this term. If Z1 is very big, then this term goes to 0, and it just becomes 2G times Z over 1 minus 0, and you get a very simple expression here. And actually, it's a simple expression that basically is the area multiplied by the velocity due to a free jet. This is exactly the equation of a free jet. So it's the same almost as having a bucket of water with a hole in the bucket. The height of the water in the bucket relative to the center of that nozzle gives you a flow velocity out of the system, and it turns out to be roughly the same. Not surprising, it's roughly the same expression here. This is the equation of water being pushed out where there's no pressure added to it to be able to push it out. And so maybe it's not surprising. We made the case about the fact that you could also, when it comes out of here, you'd think that it might be the same height as this lower height of the opening, the orifice above the bed of the river. It turns out not to be because of some so-called vena contracta effects. And it turns out that this height of this downstream portion tends out to be related to this magnitude here. And so that's useful if we know that for a variety of flow rates, the ratio of this height downstream, the depth of flow relative to the orifice under the gate, is this. And it often is quite narrowly constrained to be some number, roughly 2/3. And of course, the utility of that is that instead of, if you wanted to be able to calculate what the flow rate of this is, if you know what this standard depth of the sluice height of the orifice is above the bed of the river, then it suggests that if you only measure this height here, Z1, you can calculate what the flow rate is without ever knowing what V2 is, right? So you could substitute that that Z2 is equal to some function of A. And so now in this expression here, you could substitute the magnitude of Z2 to be able to get that. No, I guess in this expression here, right? So if Z2 really is equal to CC times A, and you know this is 0.61, then you have everything here. You just measure the upstream depth, water gauge. You don't care measuring the downstream depth, but you just know what the geometry of your dam is, and you get it straight from there. So that's, I guess, the relevance of doing that. Yeah, you can save yourself some work. So undershot weirs, overshot weirs. So as I say, if you go into the field and want to measure flow rate in a small stream, typically what you do is you just block it off and put one of these small plywood weirs across it. You can use the same expressions as we've talked before. I guess the key here is to realize that when water goes across this boundary or this barrier, either as a V-notch weir or as a rectangular weir through this rectangular orifice, then what it does is it separates as it comes off this edge here, and there's an air pocket. And this air pocket is basically at an atmospheric pressure. Yeah, really. We'll have to bring an example in. I mean, it just depends on how high it is in the flow rate. I mean, if this is really low, then I guess you wouldn't get it. But if it's high enough, well, in the limit, right? So if you take this up to here and you have a small flow coming across it, you would expect that this has momentum coming out of here. So it clears itself away from this surface because it keeps on going, just like a free jet. Well, I guess the biggest, easiest way to demonstrate it is, what do you think it would look like if it's coming out of a bucket? So if it's coming out of a bucket, do you expect it to do this? Or do you expect it to do this? So that's the demonstration. So you wouldn't expect in this case for it to be able to fill up all of this region and not have it with this. Now we could bring up the boy in Brussels, the peeing boy statue in Brussels to make this case. But yeah, you get separation. Just by the fact that momentum is carrying it out of this because it has some velocity, and obviously it has a horizontal velocity, and as we saw last time or the time before, this horizontal velocity stays constant if nothing else acts on it, but it will also have gravity pulling it down, and that's why it takes this parabolic. So there'll be a separation here. And so it basically becomes the expression that represents a free jet, which we've already seen before, proportional to some coefficient that links that. And so if it becomes proportional to the free jet, we know that what's driving the free jet is, since this is the pressure here is 0, instead of taking this upstream pressure as our gauge, we can typically take this downstream height of this as our gauge elevation, just as it would be in a free jet, right? This h would be here, uppercase H, which we've called lowercase h before, and some coefficient to correct for that. And so if that's the case, then again we can multiply by the area, which is just the width of this multiplied by its height. And if we do that, we end up with some expression. Because the height comes in here and is also present in this velocity, then it ends up just being a multiplier on two of them. So instead of being square root 2g to the half, square root 2gh times h, it's just square root 2g h to the 3 over 2. So this is just a rearrangement of that. And so again, we can get flow rate as a function of this. And so a consequence, if you like, of it looking like a free jet. We can do all kinds of sophisticated things for different shaped weirs. I'm not going to worry about that. But just maybe, yeah. So that's water pressure measurement, if you like. So it's difficult typically to meter velocities exactly, but you can do it either in closed flow pipes by measuring pressure differentials, or in open flow systems, typically by measuring elevations. The whole concept of Bernoulli, if you like, to tie things up, is the fact that this remains constant along a streamline. We can call this a total head of the system. If we write it in this form, this is always in units of meters, or length, units of length. The other way to think about this division is also to think about dividing it up into what's often referred to as the hydraulic grade line, which hydrologists would call piezometric head. Piezometric head is the total head within the system that neglects the velocity term. And so it's convenient in petroleum, geothermal, and groundwater systems when you look at flow in aquifers and reservoirs, because typically the velocity squared term is tiny. It's a creeping flow, there's no destruction of momentum in the system, and we don't care about that fact. In groundwater flow, the main losses in the system are due to viscosity, which is represented by permeability or hydraulic conductivity. And so this velocity term is replaced by another term, which is head losses, which we've talked about before, but we won't talk about now. So don't worry about that. So in groundwater and petroleum reservoirs, we typically talk about piezometric heads, which include every term except for the velocity term. And if we want to include everything, then we'll talk about the total head, uppercase H, and the energy line. And the significance of those is that in the absence of any kind of viscous losses due to fluid flow flowing in little capillary tubes in the pores of porous rock and losing energy by friction, generating small amounts of heat, then the magnitude of this energy head should always remain constant across the system. So if you take a free jet coming out of going into a hose pipe and then into a thinner nozzle, I guess in this case, the magnitude of this energy line, energy grade line, is always going to be constant. And it should always be the sum of all the individual components, the elevation of a particular point, the pressure at that particular point, and also the velocity term. If we're at point 1, we'd expect that in this, what would be the distribution of, well, any point you want to take, right? So if you take a point here, this would be elevation C1, and this would be P over gamma, which is finite if it was this point here. But if it's on the surface, of course, the pressure by definition is 0. The big tank assumption means the velocity is 0, and therefore the only potential in the system is 0 pressure, and it's made up by only this magnitude of head. So that's useful. So that gives us one reference frame. The elevation of this line as you go across the system has to remain constant as you go down a streamline. If you take a streamline from this point here and have it go through the system, then at this point you know that it's no longer traveling at 0 velocity, it's traveling at some finite velocity. So now there has to be a portion which relates to this. And the elevation, of course, would be the height to this point, and the remainder would be the pressure that would be at this point. So if you knew the velocity that was coming out of here, then you could figure out what the remaining unknown quantity was. Likewise, at this point, when it issues out of here, atmospheric pressure, all of this has to be then velocity because the pressure is 0, and the elevation is the other component. And so the energy grade line, if you like, is something useful to think about. And of course, since we've defined the hydraulic grade line as just the sum of these two, then the hydraulic grade line would just be the part that goes through the top of the portions that look at the top of the pressure distribution, right? So it's this line. So we don't really know what this curve looks like, but we know certainly at this point, if it has this velocity, it has to be this division. And we know the hydraulic grade line has to be at this point here. And so this would just be the velocity coming out of this. The other useful way to think about this, I guess the other thing that we've kind of gone up through is that the velocity here has to be lower than the velocity here, right? Because of continuity. You have the same volumetric flow rate going through this as you have going through this. So V2 has to be less than V3. And that's merely a consequence of this continuity part here. Didn't really say that, but that's the reason that this velocity term has to be increasing as we go across it. So we can make lots of kind of qualitative judgments about the system as we go across it. So what happens then if we go through this? What would we think about this? So this is the same. This snake is actually a hose now. And so you can make the same suggestions that the energy grade line has to remain constant as we go across this. Along this pipe, if it is the constant diameter, by definition, the velocity has to scale with the area. If the area is constant, then the velocity is constant. So we know that all the way along this pipe, everywhere, the velocity has to remain at this constant magnitude. If the velocity remains at this constant magnitude, then this is by definition, the hydraulic grade line is at the top of the pressure distribution or the bottom of the velocity distribution, if you like to think of it that way. And so by definition, the pressures acting in this point should be a positive pressure at this point and the elevation. If you put the height of the pipe above this, then this has to be negative. And so, or it should be lower than atmospheric, I guess, in this case. So, atmos, below atmos. And so that's actually, if you're doing experiments with water where you want to use de-aired water, so you don't want water to accumulate in your urea core sample that you're doing in your reservoir experiments, one way that you can take the dissolved air out of water is to put it in a siphon, take it up to the vapor pressure, which is about 30 feet, on a big loop, have it come down the other side, and all it will do is it'll catch the air that's pulled out of the water is kept at the top of the siphon. Ultimately, it'll break the siphon, break the vacuum in the siphon and the working of the siphon. But that's the easiest way, one of the easiest ways to get to de-air water. Yeah, so what else? We won't get to talk about a couple of the other things, but 2 seconds left. So what else do we expect as the consequences of Bernoulli's equation? Well, we might think as water goes over a bump, you get this hump to mirror the fact that this is a bump here. But actually, you could look at this and rationalize the fact that the velocity actually has to increase to go up over here. And if it increases to go through this, you can calculate what the actual dip of the water would be as you go across this, just by using both Bernoulli and also, since you have two velocities which you don't know independently, you have to link them through continuity. And so you'd expect that water flowing across this, as it goes across a hump in the base of the bed, that it'd have to go, you'd get a dip in the elevation. What else? I guess two other things to talk about. We said that we could only use Bernoulli if it was incompressible. Well, not true. We've used it for air with the jet aircraft example. It works reasonably well so long as you're not going at really high velocities like the speed of sound. So 700 or 600 miles an hour works just fine. We also said it had to be steady. And we've kind of violated that in some of the things we're doing. It worked just fine for the jet airplane with the static truck and the air hitting the truck, because if you took a snapshot of that, of the truck being hit by the air, it would look exactly the same at any particular time. If we wanted to calculate the pressure, for instance, on the nose of this submarine as it goes through the water, then we could use the same kind of thing. We might do it subconsciously, but what we can't do is take a snapshot of time of the submarine where at time t0, the flow system will look like this. At time t1, the flow system will look like this, where the velocity here was 0, and now the velocity here was 0 that was originally equal to some, or rather, the velocity here is not 0, but it's hit by the submarine, which is moving at some velocity. So the velocity initially was 0 at this point, and then it speeds up as the submarine hits it. And so instead of taking this example and looking at it in this reference frame, where you see the submarine moving across in front of you, where clearly that flow field is changing as a function of time, you do the opposite. You change your reference frame. You anchor the submarine in a wind tunnel, a water tunnel, like we have on campus. You hold it static, and you let the water flow past it. The relative velocities of the submarine to the water are exactly the same, but this yields it in a way which is amenable to us to deal with rather than the other one, which we can't. And so you have to be a little careful of doing that. Of course, I think you just assume that you can take the velocities as being this snapshot with water moving past it, but formally we actually do have to do that with Bernoulli. And finally, very last, for 2 seconds I said I was going to shut up, but I haven't, is that you can also use Bernoulli for non-steady examples. So you'll remember that last time I think we did an example where we had a tub where if you use this, if you invoke the large tank expression, then the velocity on the top is equal to 0. Not always true. If the tank gets smaller and smaller, you can't ignore that anymore. And so what you can also do is you can combine that to take care of the fact that maybe this velocity is actually moving at some small amount, which we did the calculation for. If you know that this velocity is moving at some small amount, then this velocity is also equal to the change in height in this tank as a function of time. So this is just this height here. And so it doesn't come as much of a surprise if you can relate, if we can calculate what this velocity is by, for instance, making V2A2 equal V1A1. We should be able to calculate V1. If we can calculate V1, we can calculate how the rate of this height of the tank, the level of the tank, falls with time. And you could integrate it because we have a differential, a dH and a dt. We could integrate it and we could come up with an expression that would say something about how the height of the tank would change as a function of time. And you'd expect it to be, what would you expect it to look like? You'd expect it to start off with, I know I'm going over. I know some of you are captive because you have a class here. It starts off at this as a function of time. Then what would it look like? I guess it wouldn't look like this. Would it look like this? Or would it look like linear? So the velocity out is proportional to square root GH. And so as you have less and less driving head, then the rate at which you'd lose fluid would be slower and slower. So I guess you'd expect it to kind of slow down as it goes down through here. So you can use it in systems where it's not steady. So Bernoulli, that's all we'll say about Bernoulli. We'll leave that behind for a while. So now what we will talk about, we'll talk about conservation equations. And so next time we'll start talking about the first of 3. We'll talk about conservation of mass, pouring volume into a bucket. Then we'll talk about conservation of momentum, which is really Bernoulli's equation, but written in a more general sense. And then we'll talk about conservation of energy, which we need to be able to say something about things like conversion of energy, conversion of fluid flow, kinetic energy into the energy you might want to use, like in windmills or in hydropower dams, etc.